So he started electrical engineering and received his master's and doctoral degree also at the University of Pernambuco. He was also an assistant professor at Stanford for electrical engineering in California. His recent research interest is in vehicle networking, connected objects, broadband access networks, and cybersecurity. I work quite significantly together over the last decade with Divanilson on studies. We got also a lot of exchange students from Recife. We even hired two of these excellent students, and I also can only recommend to you as well. Look also for Brazilian universities. They have excellent students and they have a very, very good education. Second speaker is David
Nascimento.
Nascimento, sorry. He is a PhD candidate in the group of Divanilson, and also he is a senior lecturer for computer architecture, network systems, and cybersecurity, and he received his master's in computer science in 2014. David Divanilson, the floor is yours.
Thank you.
Thank you. Thank you, Thomas. So, good morning, everyone. I am Divanilson Campelo, and I'm here with David, which is one of my PhD candidates, to present this work, enabling time-aware shaper on half-duplex Ethernet PLCA multidrop. And this work has been done in collaboration with Professor Steffen Bondorf from Germany. So here is the agenda of our presentation. We first make a very short introduction about the things we tackled in this work. Then we shared some words about the time-aware shaper, which is the TSN piece we bring and integrate with PLCA. Of course, we talk about 10BASE-T1S and its coordinated general access method, PLCA. We provide some details about the integration of TES plus PLCA. And we make the comparison of two approaches, TSA running on full duplex switched Ethernet versus TAS running on half duplex PLCA multidrop Ethernet. And we show that replacing full duplex switched Ethernet links with half duplex PLCA multidrop Ethernet links still complies with end-to-end deadlines, while still reducing system costs because of the sheer number of Ethernet transceivers in the network. We then conclude our work and present some hints to some of the future works we have. We all know that most Ethernet implementations today are based on switched networks with full duplex links. However, there are some challenges. For example, these links may be costly for some use cases, mainly in automotive. Data from 2020 indicate that approximately 90% of all the internal communication in cars need less than 10 megabits per second. And of course, 100 base to 1 is not cost efficient for replacing a CAN or CAN-FD legacy technologies. So the solution was 10BASE-T1S, which was standardized a couple of years ago. And as you know, 10BASE-T1S uses PLCA, and PLCA is not aware of flow priorities. So we cannot have priority-based QoS using PLCA alone. So that's when time-sensitive networking comes to the table. So TSN is a set of tools that can be used individually or combined to achieve a set of goals. And TSN includes IEEE 802.1 QBV, so sorry for the typo, it's not 3, it's 1, which is managed by TAS, and QBV provides ultra-low latency, ultra-low jitter, ultra-low loss. TS is a solution for deterministic systems, specifically real-time and safety-critical applications. So the introduction of QoS to PLCA, into PLCA, has been discussed for a while in the community, especially in the presentations from Harman and NXP since 2017 or 2018. But specifically the integration of TAS and 10-base-to-1S PLCA enables some possibilities. For example, in a scenario where Ethernet would be everywhere, the number of gateways would be significantly reduced, but eventually we would not need gateways. We would have end-to-end transmission of scheduled traffic in a scenario, for example, where end nodes or ECUs would be connected to a PLCA multi-drop link instead of connected to a bridge. And when bringing this piece, we would be closer to an all Ethernet vehicle, considering that Ethernet would be the ubiquitous in-vehicle technology. And how does the time-aware shaper work? TS is based on gate control lists. And TS deals with scheduled traffic of different priorities. There are time slots for transmissions windows. And when defining GCLs in networks, there are basically two options. Exclusive windows, which provide lowest delay bounds. They're more complex to provide. It's an NP-hard problem. They're similar to time division multiple access. And they are desired in automotive. And the second option is overlapping windows, which provide low delay bounds. They are simpler to provide. They deal with strict priority, no preemption, and it seems that they are not so desired in automotive. So here we have a very simple illustrated example of how TS works. So on the left you have the Ethernet interface with time-aware shaper with eight priorities. On the center, the GCL scheduling. And on the right, the gate states over time. So at time ID 0, only the gate for priority 2 is open. So frames from this priority are scheduled to be sent. At time ID 1, both gates from priority 2 and priority 7 are open, so we have overlap. 72, no overlap. 73, no overlap. 74, we have two gates open again, so we have overlap again, so on and so forth. Okay? So now, David, from this point, we continue the presentation.
Thank you, Divanilson. So, the integration of time-aware shaper and PLCA works only if you have sure that the integration will work correctly. We provide modeling to assure that the integration is good. So for the modeling of the time-aware shaper, is required to have some information. For example, the transmission occurs only within the open window. The guard band is considered because the transmission time of the most longer frame is the guard band of that priority, of such priority. The overlapping among windows, when you are using overlapping among windows instead of exclusive windows, in the worst case, the whole window is not available. So the guaranteed windows must be calculated. The guaranteed window is a concept created by Luxichao et al. For the worst case modeling and analysis. It's occurs within an open window, no overlapping among distinct priority queues from a single interface. In the worst case, a framing transmission can start anytime within a guaranteed window. The maximum length of a guaranteed window is the window length minus the guard band This is shown here. And the minimum length can be 0. For example, in this case here, for priority 1. For this case, in the worst case scenario, a frame cannot be sent. So this is a case where a frame must be wait for to be transmitted in the next GCL cycle. So the time-based 1S has many features. The most important one are it is a single pair, it has half-duplex multidrop, communicates up to node in a single multidrop, and has the physical layer collision avoidance. It is an algorithm that avoids frame collisions, provides bounded latency, no more exponential random wait time from CSME CD, because when using PLCA, the collisions are avoided in the physical layer and not fixed in the MAC layer. It has the optimal bandwidth utilization, mainly compared to the TDMA. No wasting transmission time, guaranteeing fairness among nodes. This is an example of intravehicular network using 7 ECUs and a TSN switch. So, how does PLCA work? The transmissions occurs within a transmission opportunity. It's a time slot called transmission opportunity. Each node has a single TO per PLCA cycle. The PLCA has 2 modes for transmission. The normal mode that a node can transmit on a single frame, and the burst mode that more than 1 frame can be transmitted. And the silent secure one, there is no frame to be transmitted. And also commit symbols are transmitted just before frame transmissions when beacon and silence are shorter than an interframe gap. The shortest PLCA cycle occurs when there are silences from all nodes. This situation is here. And also, the longest PLCA cycle occurs when the transmission of maximum frame sizes from all nodes. This occurs here, is illustrated here. As you can see here, there are a far difference between the minimum distance and the maximum distance from using PLCA instead of TDMA. This is the best of the two worlds, because when you have the time-aware shaper in the link layer, you have a good solution for traffic shaping. And when you have the time-based 1S PLCA, you have a good solution for multi-drop communication. So can we achieve ultra-low latency, jitter, and loss on half-duplex multi-drop links? How to do it? They are cyclical, but not synchronized. TAS is TDMA-like. PLCA is weighted round-robin based. So TAS has a fixed static length cycle, and PLCA has a dynamic length cycle. Both can work together, as shown in these different engines, but mistakes in the planning of the TAS or the PLCA parameters may cause packet loss or even starvation. The choice of a TAS scheduling is not an easy task. Provide a TAS scheduling to run over the time-based 1S PLCA is harder. The automotive networking are deterministic systems that require certification. You have performance guarantees. A worst-case analysis must be done to assure that all will work correctly. So deterministic network calculus it's a great solution for providing those analysis and calculate the bounds. PLCA is not aware of frame priority. All scheduled traffic flows must be complied. Not only a single frame, not only the flow of interest. All the flows must be complied with the network. A tool is required for calculating worst-case bounds. There was neither an analytical solution nor an open source tool for calculating the worst-case bounds for the integration of TAS and 10 T1S PLCA. So we provide both solutions in our work. Here we bring a graphical example of the worst case integration of TAS and PLCA. The open gates are denoted as blue rectangles here, and dashed rectangles are the guaranteed windows. When the transmission frames are denoted as colored boxes with number, and silence are colored boxes without numbers. In this example, we show that all the frames can be transmitted in the PLCA cycle. But for this case, the transmission of frame 2, from priority 2 of node 2 cannot be transmitted because the guaranteed window of such frame finishes earlier than the transmit opportunity from node 2. For this case, the node missed the TO of current PLCA cycle. It be delayed to be transmitted in the next GCL hyperperiod. For some flows, this implies and do not meet the deadline. In a worst case situation, a frame is transmitted last within a PLCA cycle. This is the worst case. This is based on the worst case weighted round-robin behavior. But note that for this case, the PLCA cycle is composed of frames from overlapping guaranteed windows among distinct nodes. The concept of the guaranteed windows is related to distinct priority queues from a single interface. But this modeling is based on the overlapping among distinct interfaces of the nodes that belongs to the multidrop. The most important information, a PLCA cycle must fit within a guaranteed window. Otherwise, a frame can miss its open window. Deadline is not met. This is a worst case situation. So we bring some recommendations regarding the integration of TAS and PLCA. TS scheduling shall have few overlapping guaranteed windows among distinct nodes. When you have fewer overlapping, you have shorter PLCA cycles and lower bounds. When you have no overlapping, that is the best situation. In the worst case, you have lowest wait time for transmission, and PLCA cycle is composed of a frame from the current node and silence for other nodes. So we have a comparison regarding using full duplex switched Ethernet and half-duplex PLCA multi-drop Ethernet. But what was the motivation of doing that? Because we are interested of answer 4 main related questions. It is possible to replace full duplex switched Ethernet for half-duplex PLCA multi-drop. How does the bounds after this replacement? It is better or worse, and how much? We did an analysis comparing the two setups using a data set from the Luxichao et al. Work. This setup has 13 distinct TS scheduling cases and 13 scheduling traffic flows. This is an example of some flows. 400 byte sizes with period of transmission of 2,050 microseconds. We have used a hypothetical 1,000 base T1S because the sum of flows exceeds 100 megabits per second. For instance, a single flow here with this scheduling exceeds the 10 megabits per second. It has 20.8 megabits per second. We done worst case analysis using network calculus. we have two important results to show here. The first one, when you take the flow of interest that comes from ES2, crosses both switches, and arrives at ES6, when replacing this setup for this one, as expected, there is an increase on delay bounds. But the increase is little. Increase ranges from 10 to 2007%, yet below the deadline. And another important result is this one, because 5 of 13 scheduled traffic flows have source and destination in the same multidrop. For this case, all 5 flows have a reduction in delay bounds when using a single hop PLCA multidrop instead of 2 hops of full duplex links. The decreases ranges from 16 to 33%. And finally, we concluded this presentation. TES and time-based UNS, the integration of TES and time-based UNS can enable ultra-low latency and on half-duplex multidrop links. It can provide reliable and cheaper solution because you can use less PHYs, less transceivers than the full duplex switched networks. End-to-end delay transmissions of scheduled traffic flows. Available models and tools for analyzing TES and scheduling over time-based UNS PLCA multidrop. This is our contribution towards an ubiquitous Ethernet in vehicle networks. It's important to highlight that this is an ongoing work. We are still working on to find the corner whether the TES and PLCA is compatible or not. In the future work, we are going to work on worst case jitter analysis of more user cases. For example, using automotive networks with time-based UNS, time-based UNS PLCA without TES, PLCA alone, and integration of time-based UNS PLCA with other TSN protocols, such as asynchronous traffic shaping. Thank you for your kind attention. Questions are welcome.
So thank you very much, David, on Divanilson. Very great presentation. Are there some questions? Please go to the mic.
Hello, I'm Philip Axer from Exxon. Actually,